Good morning, friends and dear students. It gives me immense pleasure to be here for my course Flight Mechanics. I have completed all the theoretical topics. Now I am in the problem solving exercises for the flight mechanics. Number of problems we have already solved, and we will be solving some more problems for the next 7 to 8 lectures. So be tuned for this numerical problems. It will be very useful. So today I am talking about problems on straight and the level flight. Especially I will be taking the range, how much range aircraft is taking during straight and the level flight. I am Dr. Yagya Dutta Dwivedi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In my today's class, I will be discussing about calculation of the thrust and the lift, the first question. Next, calculation the increase in thrust. Calculate the maximum L by D ratio. Calculate range in different flight conditions. So these are the topics which I will be covering in today's my lecture. I will go for the numerical number 1. A jet aircraft with a mass of 120,000 kg is cruising with a speed of 400 knot at sea level. If the drag force is 290,000 Newton, the aircraft angle of attack is 3 degree and the engine setting angle is 4 degree. A. How much thrust the engine is producing, and B. How much lift force the aircraft is providing. So we have to find out two things: how much the thrust and how much is the lift. So these two things we have to find out. So we will see here what are the parameters given here. So we will see here that given in this problem, mass is equal to 120,000 kg. We can convert it to Newton by multiplying of the G, 9.81. It is in Newton. Velocity of this thing is 400 knot. This we can convert by multiplying of 0.5144 in meter per second. So this will be 205.76 meter per second. Drag is given 290,000 Newton. Angle of attack alpha is 3 degree and engine setting IE is given 4 degree. We have to find out the thrust of this required and the lift of this system. So now we will go one by one and we will see that how we can find out. So if we take the forces in the direction of flight or V, so we can see that if this is the aircraft, okay, so and if thrust has in this direction, it is the velocity V and this is the IT and here is the angle alpha. So we can find out that this drag is equal to T cos of alpha plus IE. So this drag is equal to, in this, T cos alpha plus IE. So this is the first equation. So from here, T is equal to D by cos of alpha plus IE. D is given 290,000 Newton. cos 3 plus 4, and you will get this value as thrust is equal to 292177.8 Newton. So this is your first thrust required is this. Okay, we got it. Now we will see the perpendicular forces. So if you see here in this diagram, this weight W cos alpha plus IE. So this lift is equal to W minus T sine alpha plus IE. Okay, so W is given. So here we can write this thing that W is equal to L plus T sine alpha plus IE, or L is equal to W minus T sine alpha plus IE. W is equal to 120,000 into 9.81 to convert in the Newton, minus T is equal to 292177.8 sine 3 plus 4. So lift you will get here, lift is equal to 1141,592.5 Newton. So this is the lift, and this we got the answer here, because in the question it is asked how much is the lift and how much is the thrust. So this we have got it from this. Now I will discuss about the problem number 2. An aircraft with a mass of 2500 kg, a wing area of 18 meter square, and a drag coefficient of 0.04 is cruising with a speed of 160 knot at a constant altitude. If the pilot increases the engine thrust by 20%, calculate the initial acceleration and the final velocity. So we have to find out here initial acceleration and the final velocity. So you may assume the drag coefficient is constant throughout this flight, and the aircraft is flying at a international standard atmosphere and sea level. Okay, so it is in the sea level, and here mass is given, S area is given, CD is given, speed is given. So first we will see what the parameters are given. So now I will go with some other color. So we will see here that given so in this we will see that mass M is equal to 2500 kg and area S is equal to 18 meter square. Coefficient of drag is equal to 0.04. Velocity of this aircraft is 160 knot, or 160 into 0.5144 meter per second. Rho is equal to 1.225 at sea level. It is given. So increase of the thrust. Increase of thrust is 20%. Calculate the acceleration and the final velocity. Okay, so we know that from the equation of motion, thrust is equal to drag, and this is half rho v square s CD. So half rho is equal to 1.225, v is 160 into 0.5144 square, v square, s is equal to 18, and CD is equal to 0.04. So you will get here this value of thrust is equal to 2987.3 Newton. This is your thrust. Initial, it is like this. But in the problem, it is given 20% increase in thrust. So that Now is T2. So T2 minus D1 is equal to ma acceleration, or A is equal to T2 minus D1 divided by m, and this T2 is equal to 1.2 into T1, and T1 is here 2987.3 minus D1 2987.3, because both are same, divided by 2500. So you will get here A is equal to 0.239 meter per second square. So this is the acceleration. This is the answer for the acceleration. Now this acceleration will increase the velocity. So now I will go for the next color. I will go black. So now this acceleration will increase the velocity of aircraft. So this T2 is equal to D2 1.2 T1 is equal to half rho V square SCD. So V2 is equal to under root 1.2 T1 divided by half rho SCD. So you will get here 1.2 into T1. So T1 is how much? 2987.3 divided by 0.5. Rho is equal to same 1.225. S is equal to 18 into CD is equal to 0.04. So you will get this V2 is equal to 90.16 meter per second, or 175.27 knot. So this is the answer for this. So ratio of new speed to old speed, this will be V2 by V1. So V2 is equal to 175.22, V1 is equal to 160, it is a 1.1. So this is 10% higher than the previous one. So speed is higher. So that is the another problem which we have handled. So now we will see the next one. So in cruising flight with a constant distance, now we will see the problem number 3. The aircraft Cessna 2 has the following features. CD0 is equal to 0.022, E is equal to 0.85, AR is equal to 8.3, M is equal to 6032 kg, area is equal to 30 meters square, A is equal to 5.9 per radian, VS is equal to 82 knot, T maximum is equal to 22,240 Newton. Determine the maximum lift to drag ratio. What is the angle of attack corresponding to the maximum lift to drag ratio at sea level? Assume alpha is equal to 0. What is the airspace corresponding to the maximum lift to drag ratio at sea level? what is the maximum required thrust for this aircraft to fly. So these are the ABCD, 4 problems are asked in this given data, and we will be trying to solve this problem. So we will see here that I should start with given data. Here, if you see here that CD naught is given as 0.022, E is given as a 0.85 Oswald efficiency, aspect ratio is 8.3, mass M is equal to 6032 kg or 6032 into 9.81 Newton, area is equal to 30 meter square, A is equal to 5.9 per radian, stall speed is 82 knot. Okay, so we have to find out the how much maximum thrust is required. So I will change my pen here. I will go with red for the case A. So in this we have to find out the K, and we know that 1 by pi aspect ratio into E, 1 by 3.14 into aspect ratio is how much? It is 8.3, and E is here 0.85. 0.85. You will get the value of K as 0.045. So from here we know that CL by CD max is equal to 1 by 2 under root K CD naught. 1 by 2 under root 0.045, and the CD naught is 0.022. So we will get CL by CD maximum is equal to 15.89. So CL by CD max, or you can say L by D max. So now we got this. We will start. So they have asked the CL by CD maximum, and we have find out. Now we will go for the B. We know that coefficient of lift is equal to CD naught by K. So under root 0.022 divided by K is equal to 0.045. So this CL I will get here as 0.69. And we know that this A, that is equal to DCL by D alpha. So this alpha is equal to DCL by A. DCL is 0.69 divided by A is given as a 5.9. 5.9. So I will get 0.11 radian, and this will be equal to 6.7 degree. So angle of attack alpha is equal to 6.7. Now I will go with another color, that is the black. That is now the point C. In this C I have to find out velocity. So this velocity, we know that lift is equal to weight, and this lift is equal to half rho V square S CL. So V is equal to 2 into W under root rho S CL. So all the values we know. 2 into weight is, mass is 6032 into 9.81. Rho is equal to 1.225 into 30 area, and CL we have got here. CL is equal to 0.69. So we got this velocity as 68.3 meter per second, and we know that 1 meter per second is equal to 1.944 knot. So this will become, if you multiply by this, I will get 132.82 knot kN. So this is the another solution for this. Now I will see the D. In this D, I have to find out the minimum thrust required. It is called TR minimum. And we know that in this case, our CD should be 2 times of the CD naught. So 2 into CD naught is 0.022, so 0.044. CD is equal to 0.044. So now T minimum half rho V square S CD half 1.225 into velocity is equal to 68.3 square, area is 30 and CD is 0.044. So this T minimum is equal to 3771 Newton. This is the, so this implies that the minimum thrust to fly is about 17% of the maximum thrust required. So T minimum divided by T max is equal to 3771 divided by 22240, 0.017 or 17%. So this is the conclusion for this numerical. Now I will go for the numerical number 4. A large transport aircraft with a mass of 1,65,000 kg, an engine thrust of 320 kilonewton and a wing area of 260 meter square has a zero lift drag coefficient of 0.03 and K is equal to 0.05. Determine the maximum speed at sea level. So in this, the few problems, few data are given here. So I will write what are the given. So in this, mass is 165,000 kg. 165,000 into 9.81 Newton. Thrust 320 kilonewton. 320 into itne Newton. Area S is equal to 260 meter square. CD naught is equal to 0.02. K is equal to 0.05. So we have to find out the maximum speed. Vmax we have to find out. This is our objective, to find the V maximum. And we know the equation that for maximum A V max square plus B by V square max minus C T max is equal to 0, where A is equal to half rho V square S CD naught, and we can find out that 0.5 into 1.225 into 260 into 0.02. So this you will get 3.185. And B is equal to 2K W square by rho S putting the value 2 into k 0.05 into 16,000 into 9.81 square divided by 1.225 into area is 260. You will get 822,614.7. C is equal to rho by rho naught power 0.9. So rho is equal to rho naught. This is equal to 1. So if I put this value in equation number 1, so we can find out this problem that 3.185 v square max plus b is equal to 822,614.7 divided by v square max minus T maximum is 320,000 is equal to 0. So V max we can find out it is 285.8 meter per second or 556 knot or 0.84 Mach. So this is the problem for this equation. Now we will go for the problem number 5 here. So we will see here how these problems we can solve this problem. We have one more problem, so we will try to solve at the earliest. A small jet aircraft has the following features: M is equal to 2500 kg, S is equal to 20 meter square, CD naught is equal to 0.03, K is equal to 0.06, stall speed is 72 knot. Find at what speed this aircraft must cruise such that the engine produces the minimum thrust at 10,000 feet. Repeat part A when the aircraft is flying at sea level. So if we can do only one, another is the same way. So this we will see how we can solve this problem. So here given mass is equal to 2500 kg, area is equal to 20 meter square, CD naught is equal to 0.03, K is equal to 0.06, VS is equal to 72 knot. So we have to find out. So we know that CL for minimum drag is equal to under root CD naught by K. CD naught is 0.03 divided by 0.06, 0.707. This is the CL minimum. So at 10,000 feet, the rho is equal to 0.412 kg per meter cube. This we have to find out by the help of the table. Now we have to, I want to change my ink. So we have to find out the velocity for minimum drag. So V minimum drag is equal to under root 2 mg by rho s CL minimum drag. So here 2 into mass is 2500 into 9.81 divided by 0.412. Area is here 20. CL minimum we have find out 0.707. So we got this velocity as 178. We got this velocity as 91.7 meter per second or 178.3 knot. This is the A. Now again we will see at sea level what we are getting. So B at sea level, rho is 1.225 kg per meter cube. So V minimum drag is equal to under root 2 mg by rho at CL minimum drag. So here we will write that 2 into 2500 9.81, 1.225 into 20 into 0.707. We will get this 53 meter per second or 103.4 knot. So at sea level, you have the minimum drag velocity is less than the comparing to the high level. It is observed that minimum drag speed is increased with altitude. For both altitude, the minimum drag speed is higher than the stall speed, and we know that stall speed is given here 72, and we got first case is 178 and another is 103. Both are higher than Vs, so it is acceptable. So this design is acceptable. So now we will see the minimum thrust. Minimum thrust of the aircraft, that is called T minimum, is equal to always D minimum half rho V square at minimum D into S into CD. So if we put these values, half into under root 2 mg by rho S CL minimum drag S into 2 CD naught. If you solve this, we will get T minimum is equal to 2 into weight under root K CD naught. Thus, under root K CD naught, we can write half L by D maximum. So, T minimum is equal to W by L by D max. So that is the relation which we have to follow. Now this is my last problem, and we will try to solve in this lecture, numerical number 6. A jet transport aircraft with a mass of 100,000 kg, a fuel mass of 30,000 kg, and the following feature is flying at 30,000 feet altitude. S is equal to 341.5 meters square, CD naught is equal to 0.016, K is equal to 0.065, C is equal to 0.8 pound per hour per pound. If this aircraft flies with the speed of 325.8 knot, how far can it fly without refueling? Range, we have to find out. Determine the range for 3 following options. One is a constant altitude, constant lift coefficient flight, constant airspeed, constant lift coefficient of flight, and third one is the constant altitude, constant airspeed flight. What is the velocity such that the aircraft delivers the maximum range? Determine the maximum range for the same 3 options. So it is very big question, but we will try to solve some part of this thing we will, and then it is same as it was the before one. Okay, so we will see that whatever the things are given. So in this given, M is equal to 100,000 kg, fuel mass 30,000 kg, area S is equal to 341.5 meter square, CD naught is equal to 0.016, K is equal to 0.065. and C is equal to 0.8 pound per hour per pound. It is given. Speed V is equal to 325.8 knot. Range. What is the range of this aircraft? So we will see first the regular range, how we can find out the regular range of the aircraft. So at first we will see at A regular range, and we know that CL is equal to 2W by rho SV square, 2 into 100,000, 9.81, 1.225, 0.374 into 34, 31.54 into 325.8 into 0.5144 square. So we will get this CL is equal to 0.446. Now CD is equal to CD naught plus K CL square. CD naught is 0.016 plus K is equal to 0.065, 0.446 square. So you will get this CD is equal to 0.0289. So L by D is equal to CL by CD, 0.446 divided by 0.0289, so 15.4. Now we know that CL by CD maximum is equal to 1 by 2 K CD naught, 1 by 2 0.065, 0.016, it will go to 15.5. So now we have to see for the different cases how much we are getting. So first case is constant altitude, constant lift coefficient. So this R is equal to 2 by C L by D V1 1 minus under root 1 minus WF by W1, and if you put this value you will get all the things. 1 minus under root 1 minus 30,000 into 9.81 divided by 100,000 into 9.81. So this R you will get here 2048 nautical mile or 3794 kilometer. Same way for the case 2, constant V and constant CL, and we know that R is equal to V L by D by C log 1 by 1 minus WF by WI. So you will get 325.8, 15.4, 0.8 ln 1 by 1.03. So here you will get R is equal to 2237 nautical miles, 4143 kilometer. So these are our two cases, and if you go for the third case, so this R is equal to 2V CL by CD max divided by C tan inverse CL by CD max WF by W1 2 into CL by CD max 1 minus K CL1 CL by CD1 WF by W1. So if you calculate this and put, you will get R is equal to 2151.4 nautical miles or 3984 kilometers. Okay, so these are the things which we can further see it. Okay. Till then, in the next lecture we will see the calculate the thrust required, calculate the percentage of the engine thrust. These are the two references: Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's. Then Aircraft Performance Theory and the Practice. Any questions you can ask here. YD Dwivedi @gmail.com. Please do like and subscribe. Till then, goodbye and thank you.
Like, share and subscribe. Hit the bell icon for more updates.